We are now in section 2.3, the precise definition of a limit, and this is probably one of the first times in your career that you've gotten to see some abstract kind of talk in math here. And this is typically one of the most difficult things for somebody to understand in Calc 1, believe it or not. So hang in there, and I just want to get you introduced to this definition, and I'm not going to ever give you a very complicated function to try to understand this definition with. Just very simple functions. You can see here, by the way I numbered this example, it should have been example 12. I'm just going to call this in the notes example 11 precise lim definition or something like that. But so here's a picture. Basically, and this is the definition, if the limit as x approaches x naught of f of x is equal to some L, then the precise definition says for every epsilon greater than 0, so we choose an epsilon bigger than 0, I want to be this close to my limit. So here's the limit. I want to be within epsilon on either side of my limit. Then there has to exist a delta, which is also greater than 0, such that on either side of x naught, I'm within delta. And mathematically, we would say that the absolute value of x minus x naught is less than delta. That would imply that the difference between the function and its limit is less than that epsilon. Okay, so that's the precise definition kind of broken down in a nice picture. Let's take that to our next example, which again I misnumbered. It's as example 11 because you already had an example 11, but we will call it on the Canvas side example 11 precise limit definition. Okay, so we want to show that the limit as x approaches 1 of the function 5x minus 3 is equal to 2. Now we know it's 2. This is a very simple polynomial. It's a linear function. So for polynomials, I know all I have to do is plug in 1. So I get 5 times 1 is 5, minus 3 is 2. It's very simple because we already knew that rule. But we're trying to get you to understand the precise definition of a limit. So here's how you need to work this. You say for any given epsilon greater than 0, we have to find some suitable delta greater than 0. And you find that by eventually getting delta to be in terms of epsilon. So that if x does not equal 1, right, I'm approaching 1. So when x is not equal to 1, but it is within the distance delta of that 1, that is, whenever the absolute value of x minus x naught, in this case, is 1, so x minus 1 is less than delta, we have to have the distance between the function and its limit, f of x minus 2, less than epsilon. So we'll find delta essentially by working backwards from this guy. It tells us what delta has to be. So I want to work backwards from here. So I have absolute value of f of x minus 2 is less than epsilon. That means absolute value of f of x, which is 5x minus 3, minus 2, which when I distribute this and simplify, I get absolute value of 5x minus 5. I need that to be less than epsilon. So notice I have a term of 5 in each one. So since these are absolute value of 5 is still 5. I can bring that outside of my absolute values. So by factoring out a 5, I have 5 times the absolute value of x minus 1 is less than epsilon. If I divide both sides by 5 now, I have the absolute value of x minus 1 is less than epsilon over 5. So now I'm just going to force myself to take delta to be that number, epsilon over 5. Because remember, I had to find a delta such that when x minus 1 is less than delta, you have f of x minus 2 is less than epsilon. So by working backwards from this f of x minus 2 is less than epsilon, I can see what delta has to be. It has to be epsilon over 5. So as long as x minus 1, the distance between x and 1, the absolute value of x minus 1, is less than that delta, which we just saw was epsilon over 5, then the distance between f of x and its limit is less than epsilon. So it's sort of a work backwards thing, and that's all I really want you to be able to do at this point as far as understanding how to work with this epsilon delta definition of the limit. But it's a really important time to bring that into your mathematical career so you can start to see later on when you start to see proofs that you don't get too scared by epsilons and deltas.